Hello everybody, welcome. This will be the first video in the series about spherical geometry. And I wanted to give you a little introduction to this whole topic. So far as you know, well known, we have been studying the plane, the Euclidean plane, using in fact as little of the modern tools as possible, trying to go off the axioms and the postulates and the definitions, the terminology used by Euclid. So the first change that will happen as we move towards spherical geometry is that actually we will find ourselves needing all these modern tools. In particular, it sort of makes no sense to try to study this new geometry without all the tools that modern calculus gives us. So we're going to first of all remind ourselves suddenly about all these notions that I essentially asked you to forget about when we were studying Euclidean geometry. So what are the things that we are going to suddenly be using again? So we will use real numbers, the notions of continuity, differential, and integral calculus. And in fact of several variables. So I ask you to review some of these topics before you watch the future videos. In fact, in the next video, I will review some of them. We will not need the full power of the multivariable calculus here. However, there are a few things that will be particularly useful to us. So I'll get to this in a moment. However, let's first think about how this new type of geometry, so essentially geometry of the sphere, will compare to the more classical Euclidean geometry. So if you recall the basic notions in the Euclidean geometry, basic notions are points, lines, circles, and so on. In fact, in the spherical geometry, we of course will have a use for points. They are just the most basic geometric object there is. However, in spherical geometry, lines as such will be useless. So and let me explain in a moment why that actually is. So if you recall, in Euclidean geometry we defined a distance between 2 points as the length of the line segment that connects these 2 points. One of the Euclid's postulates told us that I can connect any 2 points on the plane by a line, and then the part of the line that's between these 2 points is a line segment, and we defined the distance between these 2 points as the length of this line segment. Or even more typical of the Euclidean approach is we would just say that the distance is that line segment. So we would not define anything called the length of a line segment. We sort of identify line segments with their lengths. So a length is nothing else in Euclidean geometry but a line segment. And the distance between 2 points is defined as that line segment. So in Euclidean geometry, basic notions are these. And the length distance between 2 points, P and Q, is defined to be the length of the line segment connecting P and Q. In fact, in the standard Euclidean geometry, one even uses the notion line to mean sometimes curve, so we should say straight line segment. And Euclidean lines could be of finite length, so he wouldn't even have to say line segment, he would just say the finite straight line connecting P and Q. But let's just think about that for a moment, how we would apply this concept if we talk about the sphere. So I'm really bad at drawing circles now, look. Let's see how good I'm with drawing spheres. Most likely even worse. So here's a sphere. You can think about it, if you wish, as the surface of the Earth. And suppose that I take 2 points on the sphere, 2 cities on the planet Earth. Okay? And I would like to ask, what is the distance between these 2 cities? So city P and city Q. Well, if I think of the sphere as living inside the 3-dimensional space, then to be strict, the distance between them would be the length of the line segment that connects these 2 points. But when you think about it from any practical perspective, that's an entirely useless piece of information. What is the length of that straight line segment between P and Q? Because if you want to travel from P to Q, you most likely do not have a drill to drill into the Earth to go along a straight line. So there is the Euclidean geometry for you. It's not as practical as it actually might think. When I was telling you at the beginning of the semester that what most people think is that the Euclidean geometry, the geometry of the plane, is the one that exists in reality, while all the other geometries that geometers talk about, spherical geometry, hyperbolic geometry, Riemannian geometry, are sort of inventions of mathematicians that do not have any realization in reality. However, the truth is quite the opposite. We live on a spherical planet. Therefore, the notion of a distance between 2 points as being the length of the straight line segment that connects them is actually completely impractical for us. Because in order to travel from city P to city Q, we cannot go along the straight line segment. We have to stay on the surface of the Earth. So we have to actually traverse some sort of arc. Yeah, so this would be the Euclidean distance. Useless for us here, while this is the arc on which we travel, along which we travel. So when you think about the sphere as a subset of a 3-dimensional space, R3, you definitely have lines inside that space. However, every such line can intersect the surface of a sphere and at most 2 points. So you cannot really travel along lines if you want to stay on the surface of the sphere. So lines are really not a concept that is useful in spherical geometry. One thing that, before I move on, that I wanted to establish in terms of terminology for our course is that people usually say sphere, and when they say it, they may mean 2 different things. They may mean a 3-dimensional object, or they may mean just the surface of that three-dimensional object. So here in this course, and in most of mathematics, when we say sphere, we just mean the surface. We mean an actual two-dimensional object. You can think of a ball that got inflated with air, and we do not treat that air as part of that ball when we talk about the ball as being a sphere. So for us, sphere is, okay, let me just write this. It's hollow sphere. So it only has sort of two dimensions. It does not have an interior. Okay, but this is actually, from practical as well as theoretical purposes, this is an important question. The question of how you can travel from one point to the other, and to do this so that it sort of takes you the least amount of time to find the shortest way to travel. Again, in Euclidean geometry, you can just travel along straight lines. They always give you the shortest possible distance. But on the sphere, you don't have straight lines. So is there a substitute for that notion? Are there curves which give you the shortest possible distance? It turns out such curves exist, not only in the sphere, but in a much more general setup of differential geometry. So in a sense, to measure distance between two cities on Earth, you do not only need the formulas for length of lines or line segments, you actually need to know how to measure length of curves. So this is something else that we are going to need from the differential and integral calculus. So we need to be able to measure lengths of curves in R3, and we will use these curves to define the notion of a distance on a sphere. How are we going to do this? Essentially, the distance, d, between 2 points, P and Q, so these are points on sphere, and this is the distance, will be defined as the length of the shortest possible curve on the sphere joining P and Q. Such shortest curves between 2 points have a name. They are called geodesics. So our first goal when we get to study spherical geometry is to identify what curves on the sphere are geodesics. They are sometimes called the distance minimizing curves. So the logical order of definitions here goes the following way. We will analyze all the possible curves joining two different points on the sphere. We will define the length of any curve inside R3. Therefore, for given 2 points and given any curve joining those 2 points, we would be able to find the length of that curve. And then we take the shortest one of those lengths and call it the distance between P and Q. And in fact, this is what the distance between two cities on Earth is. It is the length of the shortest curve lying on the surface of the Earth that joins these 2 points. So it is the length of the geodesic between 2 points. I only put here a shortest possible curve because you will see that for some points on the sphere, there are actually several possible curves that join 2 points and they have the same length. Note that this never happens on the plane in the Euclidean geometry. If I take 2 points, there is only one curve that joins those 2 points that has the shortest possible length. That's the straight line segment that joins these 2 points. Anything other than that straight line segment will have a longer length, any other curve. However, you will see that on the sphere, for most of the points, it's still the case that there's only one curve that joins them that has the shortest possible length. However, there are some points for which there are several curves that have the same length that join them. This is not as surprising as it sounds. Suppose that you want to fly from the North Pole to the South Pole of the Earth. In fact, it doesn't matter. I mean, it matters. There are infinitely many different routes you may take that will give you the exact same distance. Essentially, you can fly along any longitude from the North Pole to the South Pole, and that will give you the same distance. And in fact, a very good example to illustrate geodesics, how they're used in practice, is to look at how planes fly. So given perfect weather conditions, planes almost always fly along geodesics above the surface of the Earth. So a plane from New York to London is going to fly along a curve that has the shortest possible length between New York and London. So it's going to fly along geodesic. And that, in fact, holds for essentially any 2 cities on the surface of the Earth. You might want to ask, right, question. So is there, question, are geodesics on a sphere nice curves? What do I mean by that question? So that means given any 2 points, is there actually a nice way to determine what the geodesic between these 2 points is? And you will see that the answer is yes. Okay? Let's be a little patient and you'll see in the lecture when we actually talk about it what the answer to this question is. So I wanted to finish this introductory talk by telling you exactly which things you will need to know from the multivariable calculus to start talking about spherical geometry. And these are the things that I will review in the next lecture. However, I also encourage you to review them by yourselves. So, what exactly will we need to study spherical geometry? So one, we need to know spherical coordinates. So I encourage you to review those. Two, that's actually easy, formula for distance between 2 points in R3. 3. Formula for length of a curve in R3. And in fact, as far as these curves go, sometimes it's good to have a parametrically given curve. In R3. So I encourage you to review those, but I will review them in the next lecture.